about what?
MPI.h header file.
Yeah, you got to install. You have to install MPI itself, like OpenMPI. I mean, some of those. All right. Good morning, everybody. So this is efficient Python for high-performance parallel computing, and I'm Mike McKerns. I will talk in here primarily about how to write Python for high-performance parallel computing. So some of the things we'll be doing will be actual parallel computing itself, and some of the things we'll be doing to begin with is primarily preparing yourself for efficient parallel computing. And really, efficient parallel computing means nothing more than efficient code to begin with at the base level. If you have slow code and you put slow code out there in parallel, it's going to be slow code n times. So one of the biggest speed optimization things is actually to try to improve the speed of the code itself. When I had to do a engineering design problem a few years back, and it was a probability estimate on likelihood of truss towers to collapse under an earthquake, right? So what I was doing was generating earthquake pulses and doing elastoplastic joint deformation on the truss towers. And there's a free open source package to do this, and not the optimization part, but to do the elastoplastic deformation of the towers. And it was very good, very broad finite element calculations, and it was ultimately useless to me because it took 1 second to do each one of the calculations. And really what I was looking at doing was I wanted to put this in an optimization loop where the optimization loop is going to have to run the code something on the order of a few thousand times, maybe 10,000 times. And then I was going to put it inside of a probabilistic calculation, so either an ensemble calculation or another optimization loop. And then it was probably going to have to do that several thousand times on the code that's already calling the thing several thousand times. So the 1 second was just too long, and that essentially forced me to write a finite element solver that was faster than the existing solver. Not as good, of course, not as robust, but focused on faster to try to get it down to less than 1/10 of a second to do the same calculation, so that when I did the parallel calculations, they would get done within days as opposed to weeks, right? So it's actually a huge consideration to speed up your Python. And we're talking about orders of magnitude difference easily. So if you have something that takes 1 second to take it down to 1/10 of a second, it can be a huge improvement when you're doing it several thousand times. So we'll start there, and then we'll walk through several of the different methods. And a real goal is to be able to get to something like hierarchical parallelization with taking your code that you develop and test in your serial environment and porting it over to Parallel in the easiest way. Without changing your code very much would be the hope. And there's really two types of parallelism. There's functional parallelism, which we'll talk about first, and towards the tail end, we'll talk about shared memory parallelism. So those are two different types of parallelism. One takes your function and passes it around with one piece of your data. So that means you call a function f several times, spawned out to different processors or threads or whatever you're going to be working over. And the other is shared memory parallelism, where actually the data is not populated anywhere. It's all, there's an array or something like that that's shared across your resources, and that reduces the passing around of elements quite as much. Your data doesn't have to get passed around, but you have to worry about things like threading and having one parallel processor stomp on your other parallel processor's results. And we're a little bit spoiled in Python, and we don't worry about threading very much because we've got the global interpreter lock. But using shared memory parallel, we have to worry about thread locking. So by the end of the tutorial, we'll get through some of these things that really are in the weeds of Python. And what I mean by that is Python's come a long way in being easy to use and off the shelf for someone. And high performance parallel computing is, still there's C compilation that has to be done in many cases, so it's hard to install and then often finicky to use because we're either talking about going over a network connection or something else. Like there's a package in here that I'll talk about that is able to launch code to a cluster scheduler from your laptop and retrieve the results. That seems ultimately very neat. There's another distributed computing package that does something similar, but they're a little bit finicky. So these are not, these are things that are still on the, very much on the research cusp in Python, and could use help. All right. So I do have I did pass around a link for, if you don't get everything installed, don't worry about it so much. The most important part is almost either just pure Python itself or fairly easy to install pure Python. So there's an installation page here, and if you did get the chance to install things, you can follow along and do the examples. If not, then just follow along. The notebook pages are also up on this site, so I'll just flip over myself to my own local copy and run some of this stuff. So what I want to do start with is a motivating example more than anything else, but we'll come back to it. I do give some exercises. The exercises are, I'm not going to stop the whole class to work on exercises, but I will stop a little bit, give you time on the short ones, and then you can pick which ones you want to do on your own for the ones that are a little longer. And so this is an example that we can come back to. It's a fairly typical, I tried to build a fairly typical parallel computing problem. It's difficult. It has several levels of parallel computing that's possible out of it, and it's basically a good example that's still fairly simple and yet something that you really have to put some sweat equity into to make parallelizable. So it's a Monte Carlo betting strategy comparer. Basically, the base of a Monte Carlo strategy is rolling a die. So I have here just rolling a die, and then whether or not you win. The rolling of the die is a little bit biased, so you slightly have a better chance of losing, just a little. Then, so most of I have a number of files that are just in here. If you hit run, it should save the file to your system, and then you can run them if you like. So this one is rolling the die, and this is just going to test what happens when we roll the die. And you can see there's a bunch of ones and zeros. The ones are the wins, and the zeros are the losses. And you see there's a little bit more losses than wins. So that's perfect for a casino, right? Not so perfect for you. So I took this base code here from pythonprogramming.net and modified it a little bit. It's a simple betting strategy in the Monte Carlo martingale betting strategy. It's from Monte Carlo Yo. I've modified it so we can walk it through the several different forms of parallelism. So these are a couple of our different strategies. So we have our die roll. That's we could see we're going to be rolling the die several times, so that's quite easily something we can even think about converting to parallel. Here's the simple strategy, and the simple strategy is essentially for a number of die rolls, what happens on the next? What do you do next? So while you actually have money, roll the die, and if you win, if the roll of the die gives a plus, if it's a 1, then you win money, and otherwise you lose money. And basically, you don't make any change. We're just betting the same amount every time until you win or lose. So it's a very simple strategy to go through. And then here's the classic martingale, which is double down, but it's actually, in this case, it's a n down. You can set the value of how much you want to double down or triple down or whatever. And it's a little bit more of an intelligent or a complicated strategy. It's a while loop again while you have n current wagers to go through. If you win, then wage the same amount, and if you lose, basically you're supposed to double or n times your strategy. So that the idea is when you lose, you bet twice to recover back to where you were before. And so if you lose again, then you quadruple essentially. So that's nice because then you eventually recover everything unless you run out of money. If you have an infinite amount of money, it works really well. Not all of us do. And then there's the D'Alembert strategy, which is somewhere in between. So I'll just skip over that. But you can see that what we're dealing with is rolling a dice, and then here looking at rolling a particular die and then making some decision based on what the last die was. The simple strategy doesn't care, so that is very simple. And the other ones care about the history, and then we modify our bets based on that. And it's a while loop, so again, it's a looping construct. So that's two looping constructs within each other. And then since anytime you build code, like you saw, I ran a little test case for code. One of the very good things to do is when you're building little functional pieces of code, you want to build test code for your functional pieces of code. By building small bits of functional code, it's easier to logically understand. Like I could have put all of this in a single file, and a single function if I had wanted to, but then it's much harder to maintain, and it's actually harder to parallelize. If you write things in little tiny functions, and you can test the functions, and you can trust the functions for working, you can make sure that they're robust. You don't have to go back and refactor things as well. So that's just simple. One idea per function kind of software engineering. And with simple building blocks, it's actually easier then to go and parallelize your code. So I'm of the mind that you should always write your code first and don't try to parallelize or optimize or anything like that to begin with. But what you want to do is write simple code, which means break your code up into one line per function. Because if you do that, then when you go back, you can actually parallelize the code fairly easily. So if you follow that idea as part of development, then going to parallel is not that hard. And like I was saying, you want test code to make sure that your code is solid. So again, we're working with serial code first, and the goal is ultimately to go to parallel. Debugging serial code is much easier than debugging code in parallel. So if you're converting something to parallel and it's spraying out the code into parallel and then you're getting errors, it's often even hard to get the errors back and see what they are. So that's another reason why you want to write code that's simple, code that's functional, code that's well tested, and when you convert to parallel, don't modify your code hardly at all, right? So what we're trying to get to is learning how to build constructs that are serial, that also convert to parallel without really changing the code at all. And that way it makes it very easy to debug and test. Okay, so here's plot trajectory, which is basically going to take several of these betters, run it many times, and do a plot. Now, I don't necessarily have I don't have a numerical test here, which would be better, but I do have a visual test, which is okay if you know what you're looking for. So it's better than nothing. All right, so then that wrote it, and then this should, did I not? Must not have. I didn't execute this one. Okay, so here's a fairly typical case. The guy who just bets the same amount every time steadily loses. He's finished, so we're starting with $10,000, and he's still got money at the end, but he's lost. The modified DeLambert strategy did pretty well and then got unlucky. And here is very much so the typical case for the martingale. If you see a successful martingale, actually there's one right here, which is extremely rare. You see a successful martingale, it basically just goes straight line all the way to the end with a few drop-offs where it immediately recovers back to where it was before. But this is the more typical case. Right? Because anytime you lose, you keep betting twice as much until you crash. Right. So what we're going to do now is, now that we have those two strategies, again, both of those have options for parallel computing in them. I want to, yeah, and there again is another fairly typical case. Everybody still loses. What I want to do is now put it inside of another loop, so we have another chance for higher level optimization. And so the functions that I want to build here are run Monte Carlo for one of the strategies, check the number of players that don't go broke, so how many still have money at the end, how many actually have profited, what the total profit is, and what the percentage of the return on the investment is. Okay. And then this is going to run those. So this is another check there. All right. Okay, so now here's running the martingale strategy. You can see that it ran, I did 100 of these, and there was some success. 20% survived, 20% had money, everybody else. So if you survived, you did well, and if you didn't, you did pretty poorly. But if you look at that, the average profit is, there were winners, right? People who crashed did it badly, but there was enough percentage of people that survived, and the maximum profit is actually pretty good. So that's pretty rare. That's usually get 15% or less, and some losses, but we didn't have a lot of losers. Here's the simple strategy. 98% survived as opposed to 20, and 25% profited. So people made more people made money, more people had cash left at the end, but look at the average profit. That's not good. And the maximum profit's only $6,000, so that's orders of magnitude less than above. Okay, that's 10 times less maximum. And what we want to try to do is there an optimal value instead of a double down? Is there some percent down that can be even better? And so what we're going to do again is an optimization on top of that to give us another parallel loop. Like I said, this is something that we're going to use to come back to if we like during the tutorial, but it's a common kind of way that you'll have codes with multiple levels of parallelism possible. And since we're optimizing, we're trying to optimize. What we want to do is define a few metrics. So this is a metric for optimality in terms of safety. So 4 times the profited plus number of survived divided by 5, and we can also optimize instead for safety. We can optimize for a profit metric, which is the average profit times the initial funds. And here's again a loop, a for loop over running these things a few times. So the runs we did above, now we're going to run them several times and try to find the best strategy value. So that writes that. And so it looks like, so what it does is it basically tries it a number of times and it finds a better result and it prints it out. So it's not a perfect optimization, but essentially the value that I've gotten several times when I've done this is you shouldn't double down, but it's the optimal winning strategy is to go about 1.7 times down. So every time you lose, you bet 1.7 times what you lost. All right. So I don't know if people have written code that's similar to that, but a lot of for loops inside of Python is usually what's thought to be pretty slow. There was a lot of for loops there in Python. And we'll see what we can do about that with the rest of the tutorial. So I just wanted to use that as a motivator, and we'll also come back to it. No. We'll live with that. All right. So I wanted to talk about timing and profiling your code as a start. So here's several different, is this visible for everyone, or does it need to be a little bigger? Bigger is better. Is that better? Yeah. Okay. So here's several simple things to time. There's a list comprehension. All right. Try to go even bigger. There's a list comprehension. There's a for loop where we're doing an append, and there's a set item. So we're building a list of nuns, which nuns a singleton, so it's pretty cheap to build a list of nuns. And then we're going to use then we're going to use indexing to set the item. So they're all doing the same thing. Which one of those would you expect is actually the fastest? I tried to be fair by using things like xrange everywhere and incorporating the construction of the lists in the case every time. So here I have two things that we're going to use in timing your code. This is a nice little timing decorator, so you can put @timed on top, like a little decorator on top of your function, and what you get actually is there's a function that gets carried along with your code where your function .timed will have the time of the code. So that's and all it does is basically it calls your function within a time.time to get the start time, and then time.time minus start to get the result, and it saves it in a little tiny dictionary that has the name of your function, which you can access right down here as timed. Compare, what compare will do is it'll run two different functions several times in a for loop and check their value as they're timed, and then compare the results. All right, so there's some test code. Basically, let's check this out with the list comprehension, with the for loop, and with the set item. All right, and what we can see is that the list comprehension is faster than the for append, and set item is actually faster than the for loop also. Building a list ahead of time as opposed to appending every time is just slightly faster, probably within the noise. I don't know if that surprises anybody. Probably not. You've heard for loops are slow and the list comprehension's faster. So here's this in action, timing.timed, and we build a sum squared function. So this is not a list comprehension. It's using a generator. This is I squared for I and X. And instead of building a list, what I'm going to do is directly pipe it into sum. And the reason I'm directly piping it into sum as opposed to using a list comprehension and then doing a sum on top of it is it's irrelevant to build the list. And actually, it's slow. So one of the magic things about Python is Python's actually written in C, right? Python is written in C. You can see if you ever build the thing itself, you have to build C. And all the data structures in Python are in C. And that means the data in Python is held in C. And you will run into, as opposed to Python functions, you'll run into built-in functions. And a lot of the built-in functions are actually written in C. They're working on the C data structures. So that's another one of those things you should pay attention to, is that the fastest way to work in Python is most of the time use the built-in functions and don't use Python itself. If you're writing Python functions, you're writing slower code than using the built-in functions, basically. So one of the goals in Python is actually to pick a good data structure to compose your data in, and then not jump to another data structure. The more data structures you have to build, then you have to pull data out of C and through the high-level Python and put it down into another C-level data structure. And that's really one of the slow bits of Python. Yeah.
I'd love to see an example of what you just said, like in terms of using the built-in. Were you just talking about using like the standard Python?
Yes.
Functions like boolean and stuff like that?
Yes. Don't write your own length function. Write length. Don't write your own sort function. Use sort. So if there's something that does it, their code will always be faster than yours because the code is written in C. The only time you ever go and write your own Python is when it doesn't, the built-ins don't do what you need. I try to rely on the built-ins as much as possible. And again, I follow the practice of like this. It's very common people will have built a list comprehension and then summed it. I'm using an iterator. Iterators are extremely fast. And what iterators do is iterators allow bytecode to be built down at the C level, allows the data structures to be accessed through the bytecode down at the C level, and then it doesn't pull the results back into Python. And a list comprehension essentially has to create a new list, and then you populate that list with the code from Python, and then you're going to sum it and throw the list away. So anytime you're going to be building a data structure just to throw it away, you shouldn't be building that data structure, or you should be building a cheaper data structure. So, for example, if you had four things that you were going to build to make a list or something like that to iterate over in a for loop, one of the most common things that people will do is they'll say for I in a list of my 4 items. But building a list is actually stupid there. You should build a tuple at least instead. A tuple is cheaper. You're going to throw it away, right? Building a read-only structure that's much faster to build, that you're just going to throw away, is much faster than building a list, which actually takes a performance hit to build as opposed to a tuple. So you want to think about, is my structure read-only? Am I going to be changing it? Do I even need that structure? And when you start to do those things, you can winnow down time within Python to things that are more close to C. I mean, Python runs on pointers. Python is essentially a high-level pointer-based language on top of C, and so pointers can be really fast. The slow part of Python is actually building new data structures, which means extracting data from C and putting it into a new structure in C by having to go through Python. So things like iterators like this are good, which is why you'll see me do xrange here, and I don't do a list there. All right, so that's a built-in timer for the code, and you could see that I have sum of squared, and then I can check the time just by asking for how it was timed. Now, if you're in IPython, you don't need to have this mess of the timer. One of the nicest features, so I'm an old programmer. I've been doing Python for almost 15 years, and I hate to admit it, but I never found IPython all that useful, except for the timeit function. Now, here I am using an IPython notebook. Once the notebooks came along, it was a change of story for me. But I always went to IPython because of timeit. It's very simple, and it's one of the easiest things to do to test your code. So this, I didn't have to do anything special, and not having to do anything special is a wonderful thing. So I just wrote sum squared. It's the same function as before, and now I do a percent timeit. There's also percent timeit for multi-lines. Percent timeit is just for one line, and I encourage you to use these things as much as possible. And in this case, as opposed to the thing just running once and getting a time for it running at one time, here we have timeit where it gauges the first run and then runs it n times appropriately to try to get the best 3 times, and then gives you the average of the best 3 times. So this tells you a much better measure of how fast the code was. And I will use timeit as opposed to my intuition. So I use my intuition for how things should go in order to write it the first time, and then very regimentedly time the code, like no matter what you're going to do, because you'll find your intuition is sometimes wrong, and sometimes wrong by orders of magnitude, which is funny. And things change too. In the old days of Python, for loops were horribly slow, and they were much, much slower than list comprehensions or anything else, because what they were doing was essentially creating an object where you had to reach down at every iterations. So it's for word in words or for I in some list. And you have to have that list and reach into that list and grab an item and then drop it down somewhere else and then go back and drop it down. And that's the expensive part, right? Creating new data structures every time. But what Python does now with for loops is actually builds an iterator around for you. It builds an iterator for you around your sequence in Python that's the payload of the for loop, and it helps speed things up quite a bit. So let's look at another one of our tools that we'll start with. This is profiling your code. Here's some simple things to profile. For count in X range, look up global, right? And all this is doing is doing a lookup. So there's a global module level variable, and I'm just going to run it over several times. And how long does it take to look up global? And then here's doing this with local. So what I've done is I've made a local reference to global and then run it several times. Now this is kind of funny. Why bother to do that? And if you know how Python does scoping, what it does is all the things like XRange, they all come from built-ins. They come from a module called built-ins. And what Python does is every bit of programming space, and matter of fact, every object has a dictionary, and that's its namespace. And every little local scope of namespace, so inside of this function is a namespace defined by that function's code. And what it'll do is it'll look up a name like XRange, and it won't find it locally, and then it'll try in the enclosing scope, and then when it doesn't find it in the enclosing scope, it'll look in the global scope. When it doesn't find it in the global scope, then it looks in built-ins, and then you have your function. But what that's had to do is that's had to search 4 dictionaries for the name of that function, right? They're stored by name, and it does a lookup. It does a very fast lookup. It's one of the fastest things in Python, but it still had to do it 4 times. So here, the repeat versus repeat local is essentially testing the time it takes to do a lookup in the local scope and miss it, and then go to the enclosing scope and find it, as opposed to setting a local variable where we'll just find it the first time. Right. So does that actually make a difference? Does that actually make a difference when we run this thing several times in a for loop? And here's more. Here's the lookup of true as opposed to something. So that's looking up all the way into built-ins, as opposed to having a local lookup of true. And then we're gonna test this. We're going to test it and then run the thing. Okay. So now it's running it several times. Yeah. All right. So what you get out of this is with profiling, it tells us how long each one of those functions took. You could see that repeat local took 2.879 seconds, and this is going 1e to the 8 times. Okay, so that's 1e to the 8 loops. And then repeat itself was 3.4 seconds versus 2e to the 8 seconds. So that doesn't seem like much, but you shaved off some significant time. And here's the repeat. The second one, where we're looking up true, which had to be looked up in the built-ins versus having a local reference to the built-ins, and that's saved almost a second out of out of 2 or 3 seconds. So that's super simple, and we're saving like almost a third of our time, or a fourth of our time. Right? So you want to think about things like that, and that's just a simple local reference of something you take for granted, like a built-in. So what you'll see as people prepare for parallel code, if they write for loops or they write something, they keep local references around their looping constructs, because you do shave off time. And just imagine, like, I've saved a third or a fourth of my time, and I'm running this maybe, quite a lot. Maybe this was a more expensive thing instead of taking the nanoseconds of time the actual run takes. Then it can make a difference. All right. So again, profiling. Here's another example of programming patterns. This is got a HTML string, and we're going to have some HTML code, and this is using regex, and there's a pattern here. I won't go into what this pattern is, but it's a pattern, and we're going to use profile to profile this function, and what it is, it's going to line profile this function to tell us which lines are expensive. So it's a for loop again over searching this pattern for lines within a HTML page. So here we run this thing, and from it you can see, this is kernprof, by the way, and this says run it line by line and be verbose about it. And it says that it took 0.01 seconds, and you could see from it very easily here, this is the line that's the most expensive. 76% of the time was spent on this one line. All right, so if you're going to try to make this code faster, where do you start? Obviously, at the one line that takes 76% of the time. If you're trying to make the code faster and you're working on one of these other lines that's hit equally as many times, like this one, or like this one, it's not going to make that much of a difference. So now, what can we do? So this is the line that's the difficult one. So what we're going to do is precompile the regular expression pattern outside the for loop. So it only compiles the pattern once, and then searches the pattern several times. So that's a kind of an obvious kind of change that we could make. And when we run this thing, it's gone down from 0.01 seconds to 0.0037 seconds. And now the same line as before only took 26% of the time, and still the pattern compilation is 42% of the time, and it was only hit once. So this is, again, there's tools out there to help you not be blind about this, right? So the point I'm trying to make is these little tweaks matter when you're going to parallel and you're going to high performance parallel, and it's actually where it matters the most. If you do things like write functional code, write simple code, test your code, test it at every level, test it for speed, write it first, and then tweak it for speed in serial, as you're writing in serial, actually going to parallel is not too hard. So don't leave tools like kernprof and line profiler and timeit on the shelf. They're what ultimately will make your code the fastest. I know that seems unsatisfactorily simple, right? But it's the truth. So there's also some very nice memory profilers. They're a little bit newer. I won't go into them. So Guppy and Pimpler. So that's those tools. Yes. I like kernprof because it gives the line by line results. What's that? Kernprof should work on Windows. Okay. So I have tested the about a year ago, so I tested the install of all this stuff on Windows. It's more of a pain in the ass to get it to work, but it should. I think on the front page I did have a Windows instructions, so check and see if there was anything special for it there. Okay, so we're going to talk a little bit more about patterns. We already talked about local versus global. Let's look at staying native, another programming pattern for efficiency. So here's a few pieces of code. There's order n and order 1, right? So result for item in our iterable, insert the item in the first element, and then here append the item in the first element, and then reverse everything, right? So let's say the goal is to build an iterable where what we want to do is insert every new element in the front. Inserting every new element in the front is an order n operation, which means it takes the time to do that as the length of the list. Because what you're doing is if you're putting it in the first element, it's got to move every other subsequent element down. It's equally as good. You get the same result if what you do is you do an append and put everything at the end, and you don't have to move anything over. And then you reverse the list at the end, okay? That's actually an order 1 transition because you only care about adding the last element. So I would expect this one, the order 1, to be much faster. And it's using built-ins in both cases, so that's a fair comparison. And there's use a list, so this is taking whatever the iterable is, converting it to a list, and then reversing it. So this is saying, well, what if I had something that wasn't a list and I wanted to convert it to list just to get it to reverse? So then I'm going to compare both of those, and I'm going to compare order 1 versus order n, compare converting first to a list versus not, and using whatever the thing is. And here we can see that order n versus order 1 for 100 elements, order n versus order 1 for 100 elements is 1.5 times for 1,000 elements. And by the time we get up to 10,000 elements, this guy is a 23 times speed up for putting things as an append and then reversing. Okay. There's this case which says, well, whatever I'm doing, I'm going to create a list first, so converting to a list, and then comparing that with order 1. So let's say you had something that wasn't a list, and then so range is both a list both times, but still I'm going to convert this to a list anyway, and that times essentially the how much times it takes to cast something to a list. So let's say you had a set or something like that, and you wanted a list method because you wanted reversed. How much time does that casting take? And you could see that it doesn't take that much time, but so it doesn't change the time it takes terribly much percentage-wise. But what it does is it's actually a huge amount of difference. It's an order of magnitude to 2 orders of magnitude of a slowdown to create this new object, right? And that's what I was saying at the beginning. To cast something to a new object, takes an incredible amount of time. It's one of the slower things in Python. If you have an iterator and you go through an iterator, it's fast. But if you actually have to create a list, just temporarily, or a set or something else, just to throw it away later, it's one of the biggest slowdowns in Python. So here's pointers versus copies. Again, with the same idea, is it, if we can we get away with not making a new structure? So here's a range, and then what we're going to do is extend the list by range itself. Okay, so that takes a list and adds more. It's a variable length array essentially in C, so we've added more to it. And here we have a double concatenate, which this has a list, and now it creates a new list from two lists. The difference being this was a list that you don't use, people use plus more often to concatenate lists. So is it more expensive to build a new list from an existing list being added to itself, or is it more expensive to take a list and not create a new list and then add n number of elements to it? So remember, I'm putting it out there that one of the most expensive things is creating new objects. So I would expect extend to actually be what takes less time. So then we run this, and you can see that for 100,000 times, the double concatenate is worse. Okay. It starts out, though, just about the same speed, and extend is a little bit worse for small items. But as soon as you get a little bit larger, there's 100 and there's 1,000, then you start to do better without having to create the new list. Because again, what Python has got to do is it's got to take those objects out of C, put it into Python, and then put it into a new list down in C. As opposed to extend, which is a built-in and can move some of those items over. It doesn't have to create half of the new items into a new array. You know, when you look at something like this, you see 65, 67% of time saved. And so these are rational numbers if you're talking about parallel computing and having something run 10,000 times. You're, again, with this simple little bits of code analysis, saving yourself 65% of, well, not actually 65, 45% of your time, or 35% of your time, whatever my math skills will allow us to calculate. All right, so choosing the right container is a big thing too. So here's converting to a list from an iterator, and then checking whether n, a random number, are the last number actually. So it's the worst case scenario for a list. Checking whether or not the last number is in that list. And then we're going to do the same thing and search a set. We're going to take X range, convert it to a set, and then check whether or not the number is in the set. So which one of those do we expect to be faster? Sets, right? We know looking in a set is much faster because it's a hash map essentially, or it's the keys of a hash map. Searching through a set is order 1, searching through a list is order n. And this will take a little bit, but you can see that's the case in small numbers. You actually can get sometimes where the list wins, but really when you go larger and larger, the set wins. All right, so now let's do it again, but let's say, let's take a look at this. If you have X is a set, and then we time whether it's in a set or, okay, let me see, make sure I did this right. Yeah. Okay. So yes, this the set wins when it's big enough. But one of the things that's happened here is we've converting both of these. We convert that to a set, and convert that to a list, and then search. Here, yeah. I'm going to do it again where we convert to a set ahead of time and then do the search, and then convert to a list ahead of time and do the search. And so the timing is not included in the search. We don't have the timing in the search. You could see it makes a huge difference. Here's the set is 55 nanoseconds, and looking through the list is 152 microseconds. So that's a huge difference. And not as different as actually this was. What this should tell you is the construction of a list is a little bit cheaper than constructing the set. You can see that it costs more to construct the set for small numbers. And even in this case, where we're doing it 1,000 times, construction of the set, using the set didn't gain you as much as you would have thought it would by looking at what people typically say is the set's going to hands down beat this thing. Now, one of the things is if you follow the rule that searching through a set is a order one operation and list is order n operation, and you have things in a list, they're in a list already, and you got to convert to a set, what do you think is going to be faster? Converting to a set and then searching order one, or just using the list? Just using the list will probably be faster. Right? So yeah, it's got to build the index, it's got to build the hash. That's right, it's got to add all the elements to the set. That's exactly right. So you got to think about also each operation that you're doing has overhead. And two of the most expensive things are building a new object, and the only thing that's really even worse than that is doing an import. Right? An import's expensive because it's building a new module object. So anytime you can avoid an import, you should do it. And building a new object is the same way. Anytime you're building a new object, you've got to break that barrier from Python in C to Python in Python, and constructing a new object in C and stuffing it with data, essentially. So those are the things you really are trying to avoid in the core of parallel computing. All right, so if you feel like giving it a try, there's write code that calculates the sum of all squares for numbers 0 to 1 million. Do a loop that adds with plus equals, and do it with a list comprehension, and then use a generator comprehension. Try it with range or x range. Try it with different small numbers, and see what you get. So if you'd like to do that, then I'll give you a little time to play with that. Not too much, but a little. Yeah.
I had a question. You're comparing order one using the list method.
Yeah.
I think you might have the division for use list versus use order one. Ratios result.
So here, compare O1 to the list. R1 is the list. Oh, okay. I do. I think I said the right thing though, but it's just printed right I was saying the list is more expensive. The list is more expensive, but it's just this is printed. This should be, and you're right, like this. It's just the,
So
that's wrong.
The used list is a smaller number being divided by order one.
Yes, that's right. Because the thing that I'm showing there is it's a list being converted to a list, which doesn't do anything, as opposed to converting it to what does order one do? Yeah, this one, which doesn't care whether it's a list or not. So the idea is yeah, that's right. That's the difference between the creation of it being a list and iterating through each of the elements. So thanks. All right, so for those of you who had a keen eye, I think I also did exactly what I asked in the exercises right below. For those of you who are not into doing it yourself. We call that cheating. Or leveraging existing code. All right, so I know that wasn't an awful lot of time, but this was also fairly short. So you can continue to play with it. We actually have a scheduled break coming up pretty soon, so if you'd like to continue to test within the break, you can. So we'll look at here's the code itself. There's a generator. Actually, I have it right here. here's a generator, sum I squared for I in X range, the list comprehension, there's the generator versus building the intermediate list, and then doing it within a for loop. All right, so which one of those do you expect to be the fastest? Expect the generator to be the fastest, probably, right? That's what I would expect. You're told that for loops are slow, and that's been the case in Python for quite some time. However, let's look at what we get in the results. So for 100 elements, we get the for loop is the fastest. For 1,000 elements, the for loop is the fastest. For 10,000 elements, the list comprehension is the fastest just slightly, the for loop being second. And that's probably noise. And here in whatever the largest number is, for loop is the fastest. Surprising? Yes. So the reason that this is the case is I squared for I in some big number is really, really cheap to calculate. So what you'll find is for loops used to be dog slow and inefficient, but since they've started to use a iterator as the payload, basically the byte code gets converted. So within that for loop, for I in some iterator is actually what you get. And actually, any time you have for I in an iterator, the for loop will be faster. It used to be only if it was I squared and it was something cheap and there was maybe 30 or elements or less, and that was the way it was for a long time. But now I've actually, over the past 2 and 3 years, started to convert to use lots of for loops. If you use a for loop with an iterator as the payload, like X range up there, or if you can write your code in such a way that you have I squared for I in range, like I had in my generator, and it was actually doing something and forming a generator, or you perform an operation that then will give you a generator or iterator, and you do a for loop over it, the for loops are very fast. So don't write them off that easily. I've actually had to go back. I have some Python modules that I recently went back and unrolled a lot of my list comprehensions and replaced them with for loops, which seems like an odd thing to do in Python, right? So you should be aware of that, especially if you're doing multiple steps. If you're doing multiple steps, or you can come in with an iterator on a for loop, the for loop is fast. Yeah.
So you said when the payload's an iterator, you mean a built-in iterator?
A built-in.
Because anything in a for loop is going to be iterable.
Yes. What I mean is, what you do when you have a for loop is you build a sequence, right? So the worst thing you could do is, if you have 4 items, set them in a list, and then throw away the list. Better is to put a tuple around them. Even better is if you're doing something with them that the step above yields you an iterator at the end. Then you don't make any intermediate construct that you throw away. And also, what you can do is not take that result from above into Python and just keep it down in the C layer. So a built-in iterator is the absolute best. So enumerate and reverse and X range and things like that. But it's also really good and quite efficient if you're doing multiple loops or multiple processing of something that's iterated or a sequence, and you actually don't yield back to Python function. You keep the thing above as an iterator or a generator. The for loops will be fast on that stage. So as long as your payload is an iterator, generator, you'll get a fast for loop. Yeah.
So when I first wrote this, I used x star star 2, which is about 3 times as slow as x star x.
Right.
Why?
I can't tell you why one's faster than the other. I think, I mean, I did know there was a difference, but I don't know actually why that one is slower. You'll find actually another thing that I don't test here, but that may be surprising is the square bracket lookup. Square bracket lookup as an index ends up being much faster than if you were to call the functional form of like get item. You think the square bracket is parsed into get item, but it's parsed in where it's got to do. It's parsed in at the parser level, and it's actually faster to do lookup with the square bracket than it is to call the functional form. So there's some funny things like that in Python where they've actually optimized the short parsed forms of things like square brackets end up making a big difference. For native structures, absolutely. Absolutely. The difference is the code's interpreted in C versus the code calls a Python to call a C, but for your own class it would make a difference. Yeah.
Why was the list comprehension form faster than the generator form?
That's a good question. I think, let's see here, how much did it do of a difference? Okay, so list comprehension being faster. In part, generators are more expensive to build. So it's, if you look at it with 10 times, with 1,000 times, it's always the generator is being slower, right? The generator looks like it's the slowest, except this one time here that it's in 100,000 times or whatever it is. So yeah, the generator, again, against your instincts is slower. And I don't know. I mean, that's why it's worth the time. That's why it's worth the time, these operations, right? So, and it does change over the versions of Python too. Like generators, I could guarantee generators were faster, but then things changed because they have different levels of overhead, and someone will write a different parser function that slices into a different level of the C. So, you know, we'll run into things like here that people have asked that I don't have an explanation for. I mean, I have some idea, but I don't. And I will do exactly the same thing that I'm telling you to do, is you have what you build up as instinct, and then ultimately the best thing to do is time it and find out. Yeah, you have something.
I was just going to say it might also have to do with the fact that you're summing the results. You might be able to do some.
I don't know. Some works on an iterable, so I'm not sure. It's
Winding up calling some the same number of times, aren't you?
You're getting the results differently though. You're summing over something that in the sum it's got to pull off one item at a time, and the other one it's sum acting on the whole thing in memory. Again, I don't know, but it's worth noting that it makes a difference and checking it out like that. All right, so we'll get into vector programming. I guess we have a scheduled break of 15 minutes for food or something like that. So we can come back in 15 minutes. Okay, so let's start up again. So let's start up again. So we're going to go from Python to vector parallel programming, which is essentially Numpy. And Numpy is one of those packages that if you have an object as a Numpy array, then you can do a lot of fast things. But you also have to look into the consideration, and again, I'll mention the consideration is going from a list or some other Python structure to a Numpy array has two of the most expensive things you're going to do in Python. One is import a package, and Numpy's import is about 1/10 of a second. So you're going to lose 1/10 of a second. That's pretty significant, right? And number two, so right, if you're farming out that package, Numpy, to a different processor, and you've got to do the import of Numpy, it's 1/10 of a second straight out on everything you do on every processor. You do it once, right? But still, you start out with an overhead of 1/10 of a second. And I'm not saying it's not always the wrong solution, but it's something you have to be aware of. And then second, if you converting your data and you have it in a list, you got to build a Numpy array. So that's building a new data object. So before you get to the GUI speediness of the Numpy vector programming, you've got to go through two of the more expensive things, which are the import and converting to an array. So trying to avoid that is good. So I use Numpy for some. I use Numpy a good bit in my programming for parallel, but I also very cautiously avoid Numpy when you don't need it, especially if what you're going to be doing is serializing a function that's going to be sent off to another processor and it's got Numpy in it, and you're only using Numpy for a particular built-in when there's a perfectly good Python built-in that does almost the same thing, you will almost always lose with going to Numpy for that case. So again, beware of that kind of thing and time. So here's Numpy. So if you have just a basic, is if you have an array of 1, 2, 3, 4, and there's 5, 6, 7, 8, you have a new array that's built a plus b. You have a times b and a squared minus 2b plus 1, and they do element-wise operations. And actually, I don't know if I have this timed in here somewhere, but one thing that might be surprising, and see if I remember to do it, if I don't right now, is Numpy also has plus equals operations, right? Numpy has plus equals operations, and that allows you to do addition and multiplication and whatever in place. The plus equals operations are significantly faster, I believe, if I remember correctly, because you're not actually creating a new Numpy array. And that's a big difference, is creating a new data object. So if I don't have it, we can check that out. So one of the things you get with Numpy arrays is you get built-in methods on a Numpy array, which the goal is basically to not use max and sign from math in Python math, to use Numpy's built-in methods. And what this will do here is it'll actually take the Numpy data object A, it'll call the sign or the max method on it, it'll call it down deep in the C layer essentially, and then return to you a result finally in Python. So these methods, these ufuncs, they don't require bringing the result back into Python, and they also operate on each element down at the byte layer. So that's good. There's Here, here's several different methods for doing like addition. There's hstack and there's adding, so concatenation and adding, and accumulation. Okay. So there's a lot of what you'd like to do with an array in Numpy. So we're going to start with an array 0 to 8 by 2, and this is nice because it's a range, and what that means is we're just going to directly build a NumPy array as instead of building a list and then converting it to a NumPy array. So a range should be faster than doing the conversion. And then there's a I wanted you also to be aware of np empty. So what np empty is often very good for is np empty allocates an array. Right? So any of you who are C programmers, one of the ways you work with an array that's growing in size. So by the way, NumPy arrays, when they're built, they lock in the data type. If you build an integer array, you can't put floats in it. It stays integers. If you build a float array, you try to put anything that's not a float in it, it will cast it to a float or fail. And they're fixed length. Right? So they're just like C arrays. They're C buffer memory, essentially. Matter of fact, the data is not even in Python. There's pointers to the C objects, and it's stored in C. So that means if you have growing data, if you have data that comes in and you want your NumPy array to expand, you actually can't do that. What you'd have to do is keep creating new NumPy arrays. So just like the C strategy, one of the things that you can do is build an empty array of the appropriate size. And the easiest and cheapest thing to do is build an empty array that's actually empty, unallocated. So it's allocated memory, but uninitialized memory. Allocated, but uninitialized memory. And then fill the object up with the data as it comes in. And what you can do is, you could see this array D right here is, I'm going to be slicing on this array. I'm going to be slicing on the array right here. And the slicing on the array is only going to give me the values that are actually filled. So it'll look just like I have an array with no uninitialized values. You don't see the uninitialized values there. And another thing that's nice in a NumPy array is that slicing and indexing is done by reference in general, which means you're not creating a new NumPy array. So that's very cheap. Anything that's done with pointers is cheap, and a ranged slice or a regular slice does not create a new list, does not create a new array like it does in Python. It would create a new list in Python. So that is ultimately very fast, and it's a nice trick for building an array that grows, essentially, or looks like it grows. So here's also stacking. That's a vertical stack. All right, so that's just some basic kind of things you can do. Let's look at pointers versus copies. So here's an array E. There he is. And what we're going to do is change the shape and then change the shape by reshaping. So those are two different operations. The first one is taking the array that was up here and converting it to that. Going from a 2x4 to a 1 by 8 and then going to a 4 by 2. The first one, now I didn't time it, but the first one is faster than the reshape. And the reason it's faster than the reshape is what actually a NumPy array is in NumPy, in Python, is just a very simple index structure. The data is held in C, and there's a pointer to the data held in C. There's also a pointer to the data type, which is a C data type. And from Python, there's only a few small index values. One is the shape, and the primary one is the shape. It gives you the number of dimensions, and it gives you the strides and for each size. So that tells you what the view of that C array looks like in Python. Changing the shape of a NumPy array is, since it's only a view on C data, when I'm doing this and I'm changing the shape, which is a tuple that's actually held within the NumPy class, I'm not moving any data around. I'm just changing an index. Yeah.
Is the shape of the underlying C structure a one-dimensional array?
It's a 1D array. It's
Always 1D array?
yeah. It's a 1D array, and essentially what you have is if you had a 1D array like the one right above the blue, 1 through 8, it's a single bit of, as best it can be, contiguous memory. And what you get from Python from an ND array is just indexing. So every time you move over a column, it's 4 bytes or something like that for an integer. And every time, in this case, you would move down a column, it would be 8 bytes over. That's one of those things that if you have a million by 2 NumPy array going operations down, that it's moving over 4 bytes every time is actually very quick, but every time it has to go down the column and go over a million, it's actually really slow. Well, there's no way to reshape the underlying structure, no, but you can index it. One caveat on that. If you've built it already, there's no way to reshape the underlying structure. One of the things that people will do is they'll change the shape, transpose it, etc. But you still are working on the thing that may be laid out in memory incorrectly for you. Python NumPy does give a keyword called order, I believe it's called, order, and you could pick C or Fortran, yes, and that will change the way it's laid out in memory. But it's always one-dimensional, yeah. All right, so reshape actually builds a new array, and shape doesn't. It modifies the view. So changing shape here is really fast. This is another operation in NumPy that's going to be super fast, is taking a transpose. Taking a transpose of a 4 by 4 or taking a transpose of a million by million, it costs exactly the same amount of time. You can try it yourself. You can time it, make a million length array and take the transpose and do the same thing with a 4 by 4, same amount of time. The reason is because the data doesn't actually move. It's a pointer in Python to the C data, and the thing that gets changed is actually the dimensionality gets flipped. It flips the dimensionality, rows and columns get flipped, and the strides, which are how many times it's got to walk over on the one-dimensional array to get to the next row and then get to the next column. Those two numbers get flipped, and there you have your transpose. So you want to look at that kind of thing as if you understand what's going on with NumPy and the operations it's doing, it'll help you determine what's a fast operation, at least have it in your intuition. And then here, flatten, there's several operations that flatten out a NumPy array. Some of them make copies and some of them don't. You just have to know which ones do. So it's worth noting which ones make copies and which don't, and you can test them as far as time. Creating a new NumPy array is going to be expensive. but working with a pointer, which it provides, where it doesn't create new data, there's a lot of NumPy operations that don't. Right. Well, that's important. So one of the things you'll see about NumPy's indexing also is you don't need to. It has multi-indexing. You don't need to give two indices like you would in a list. And the reason for that is, again, it's this index operator that's being reconfigured, and it's trying not to return. Oh, okay, so in Python, every time you do an operation, it produces an object. So if you do an index, it produces a new list object, or it produces a new integer. And so every operation that's done produces a new object at every stage. And NumPy tries to make things faster by compounding the indices together, so you don't have an intermediate object that you have to build. It directly goes down and indexes out the value and returns it to you, or you can set a subset of the values. So slices, this is regular indexing. This is slicing. I'm going to slice the first element in the rows and 0 to 2 and replace it with this value. And that changes things in place. This doesn't cause a new an array to be built. It's just replacing several of the elements. Here again, I'm not creating anything new. 0 to row 0 and column 0 to the end by 2. B will have B will be a pointer back to the original data in C. So this was very efficient to create. And here's a add in place. I'm going to add -10 to B and put the result back into B. Okay, and that is very efficient, and just as well as you can do plus equals. And plus equals and add take different amount of times, and you should check which one of those is faster. And you could see that by changing, I guess by changing B, I also changed D as well, because it's referring back to the same data. So that's something you have to be aware of in NumPy is a lot of the operations are built to be cheap. So they're built to be inexpensive. They're built to not create new data objects. So they can be very fast because they're just dealing with small number of indices being changed that reference actually the data in C. And the caution is that you might stomp on your original data, which you unintentionally will mangle. So now let's look at a little bit of timing then. I have NumPy A range, so I'm going to 1e to the 8. I'm going to do a transpose. I'm going to do a slice, and then I'm going to add in place. So none of those should create, oh, sorry, that's not an add in place, that's just an add with a transpose. So the first two should not create any new new arrays, and the last one will. So this is 1e to the 8 that's being transposed here, and you can see that it only took 147 nanoseconds to do the transpose of 1e8 elements. That's really fast. That's not moving any data around whatsoever, which might be unexpected. Here again, this is a slice, so this is just changing an index and a pointer. It's 222 nanoseconds. Again, that doesn't take very much time. And then here is a transpose, which doesn't take very much time at all, but adding two elements together, which ultimately then does build a new NumPy array that takes more time. And then NumPy also has some very flexible operations like where, which allow us to do irregular indexing, and these guys all produce new. They produce copies of your results. While you can do much more flexible things like say x, where the remainder of x divided by 2 is not equal to 0, is equal to x, where the x remainder of 2 is not equal to 0 minus 1. Right? That's a perfectly legitimate slicing operation. And it's not as efficient as you would have liked because you actually have to create a new array here. But that's what you get for flexibility. So let's look at one of the nice things that in so that's the basics in NumPy, and once you have that down, then you could start to do nice things with NumPy. So here's a particular operation that's quite useful. It's called vectorize. And let's say what you're trying to do is you're trying to write something in NumPy that's vector parallel. And actually writing something in NumPy vector parallel is hard. If you're not doing a vector parallel operation, then it might not be efficient to go to NumPy, because if you find it hard to write in vector parallel, maybe it's something that doesn't fit into vector parallel. We'll see an example of that later. Okay, so sometimes also Python's good about rapid prototyping, and sometimes in parallel computing you just want to get the answer and you want to get it fast, which is one of the reasons why people use Python over C in high performance computing. C is almost always going to give you a faster answer, but the Python is easier to get there first and program and get the function and get the code going. So NumPy has one of those things is if it's not trivially or easily written as a vector, as a matrix or an array, you have to work at it. And working at it can be expensive in the cost of your time. And I found I've used this trick, NP vectorize, a couple times when I couldn't sit down and figure out how do I convert this thing to parallel. I said, okay, I'll give up. I'm going to do it the easy way. And the easy way is let NumPy convert it to parallel for you. And all it is basically, let's say, look at this function where it says that the sinc of x, if x is equal to 0, then return 1. Otherwise, NumPy sine of x over x. Now this part is vector parallel, but this part isn't. The x is equal to 0 isn't vector parallel. Now you can use where and figure out how to do that with where, so you would make this a NumPy function. But let's say this is what your code looks like and you want to vectorize it to run as a NumPy function. You can just say np vectorize and vectorize this function, and you'll get a new function called sinc, which is vector parallel. And that works as a decorator too. I could have said at vectorize and then just converted this to NumPy. And it'll be faster if you figure it out and write the NumPy code. But in the sense of rapid prototyping and getting the code out there, vectorize can help you so that it can help you just get it off the ground. So it's a worthwhile trick to know that's there. Here is map of the sinc function. Okay, so what I'm going to do is now over some x, call map of this sinc function. Then I'm going to call the sync function, which was NP vectorized, and then I'm going to look at NumPy's built-in sync function. So map of the sync function is essentially what NP vectorize is doing. Okay, so map is using Python's map, which basically says take this function and apply it to every element of x, and you get 38.4 microseconds. And here's the NumPy function that you built with NP vectorize, and it's actually slower than using map of this sync function. It's slower probably because of the overhead that it takes to go to NumPy, but it's also slow. Both of those are much slower than actually doing this with the NumPy built-in. Here's the sync of x, which is now done at the C level as opposed to the code up here, which is not. All right, so again, the built-in wins, but while this is a nice, convenient way to write in terms of function in NumPy, you might not expect that the map function would beat it, which is essentially what vectorize is doing. All right, so if you like, one of the things you might want to do is go back to this. The first motivating example, and look at role, strategy, and trials. See if you could figure out what the hotspots are. Basically, do timing, and try to make improvements. I would say try converting to vectorized versions of the code. And what's going to happen is it's very difficult. While loops don't convert very easily to vector parallel, but embarrassingly parallel things do, like the simple example. The simple strategy does. So I'll let you go there if you want to try that, but I'm actually going to skip that. The solution is here if you'd like. Okay, so programming efficiency is testing, error handling, etc. Functional programming becomes a gateway to do parallel computing. So we have things like add and squared, and you could see in a list comprehension, there's a doubly nested list comprehension here. For you read this as for JK in zip x and y, add j and k together, and this is in a generator, and then for I in this new generator, give me squared of I, and then return it as a list comprehension. All right, so this code and this code are doing exactly the same thing. There's this, which is a very common way to do this double nested for loop. People will write a generator, and people will then nest it inside of a list comprehension. I actually don't like that. You can write the generator separately and leave a name for it and basically a pointer reference for it, and then drop it inside of the list comprehension. It's a little bit easier to read, a little bit easier to debug. But this is also the same thing. So map of squared on the map of add of x and y. Okay, map of squared on the map of add and x and y. Those lines are identical. So then let's time both of them, and what you will actually see, they give the same result, and the second one with map is faster because there's overhead in building the list comprehension and there's overhead in building the generator. The map looks cleaner and the map is faster. All right, now that's not always going to be the case, but it generally is often the case. So I build a lot of this code which you think you'd like to do to go to list comprehension and generator comprehension, and I build them with maps. There is iterated maps. If you go into iter tools, there's iterated maps that produce an iterator as opposed to a list. We'll see that. And the nice thing about maps is if you have maps, you can directly go to parallel computing. So one of the things a lot of the parallel computing libraries provide are maps. There's two things that are standard structure. When you have a parallel pool of workers, you're going to get a map or you're going to get a pipe. So pipe is apply. Apply, that's take a result somewhere and push it over across a pipe, a process boundary. And that's the same as calling a function across a process boundary. And then there's map, which is pushing the function across several process boundaries in a pool. So it's n pipes, basically. And here's multiprocessing doing the same thing. Here's map of squared of range 10 and a thread pool. This is a thread pool from the multiprocessing library doing squared, where it's doing squared over range 10 in parallel over several threads. And you notice the parallel one is much slower, right? Parallel is much slower. The reason parallel is much slower is because the payload, you think automatically, hey, I'm going to do in parallel, it's going to be faster. It's not. It's not always the case. What you find is as you optimize the code to be faster and faster, you need parallel computing less. And the overhead for going into parallel is high, just like the overhead for going into Numpy is high. So anytime you do a parallel map, people are often surprised that it actually is expensive. It's got some overhead cost because what it's going to do is it's got to now spawn a number of threads, and it's got to take that function and serialize that function and send it off to the other threads. And processors are even more expensive because you got to spawn a Python on each one of those processors and then send the function out to each one of those processors. And it's more expensive in the higher parallel as well. So there's a penalty essentially you pay as overhead for doing business with parallel, that if your code is actually cheap, you don't need to go there. So that's another one of those things you should time to see if it makes sense. Don't just assume that going to parallel is going to be faster. And here, let's look at sleepy squared, where I'm going to sleep for 1/10 of a second and then essentially do the same thing. So this is the same exact code as above, but the payload takes 1/10 of a second. And now to do it 10 times, of course, it takes serial 1 second. And to do it in parallel, it takes 200 microseconds. So it's faster than in parallel. But you can see that the overhead cost almost, so this is going to be 10-way parallel. It's 10 threads. It probably took half of the time to set everything up and half of the time to compute it, actually. All right. So here's a sanity check you can do in for our parallel map. So we're going to do a squared, and then test squared actually gives us the same result. And then what we want to do is do a nose test. So this is the reason I bring testing up is that, again, it is possible when you write these things. You saw going to parallel when I wrote things in terms of a map. Going to parallel was trivial, right? Going to parallel was trivial to do in this one particular case. And if you're writing things, you should write your code in the serial case, and then and write test code to convert to check that the parallel is going to give you the same results. But really you should be testing your serial code, and if it doesn't take anything but a replacement of a map function, then the only thing that can go wrong is serialization or timing. So let's look at something like this, which is error handling. So I'm going to call sleep, where I import sleep. Sleep is not a module, so it's going to fail. So here's map of bad of range 2, and there it throws an import error. Now, if I was to do this in parallel with the parallel map, what would it do? It would hang on me, essentially, right? So the goal, the point I'm trying to make there is you want to be able to debug, you want to be able to do your code serially, you want to be able to write your code serially. Map functions are fantastic for these kind of things, and apply. Again, the other thing that comes off of a pool that people don't use a lot is apply. It's a pipe. It allows you a single function call across a process. And both of those, you can write your code in serially, and then do the conversion right to parallel just by replacing map or pipe in a lot of cases. So here's less bad, okay? Here's less bad, and this guy doesn't fail. And the reason he doesn't fail is I catch the import error on sleep. All right, I catch the import error on sleep. Now, why do I bother to do that? Why do I bother to do that? Let's say if you're in a parallel environment, and you're doing something where you're reading 1 million files, and one of the files in this blocking map fails, and you have an IO error or a file read error or something like that, and you're not going to get any results back. Your parallel, if you're doing a blocking map like I've showed thus far, you're going to get no results back. Your pool is going to hang. You won't get your results back because with a blocking map, all the results have to finish first before you can get any results back. So a common thing to do when you're doing parallel computing is be very careful about having try and except statements in your code. And you want to return something sane. So if you're trying to do a sum of elements, and you're doing something where you can do a sum of elements, maybe you return a nan as opposed to letting an error get thrown. Right? And the reason you might return an AN is then you can discount it. You can count the number of times there were failures. There's a NAN because it was not read. You can do the sum without, if you use NAN sum in Numpy, you could do the sum without worrying about the NANs. And most of all, it doesn't fail the parallel computing. You'll still get results back. So you want to think about those kind of things. In parallel computing, you don't want that error to be thrown because often it will hang your code. So I often will build in things like that return either nuns or nans or zeros when it makes sense. And again, it seems silly, but another one of these things that is extremely helpful is to run sanity checkers like PyFlakes and PEP8 and on your code, because if you have a typo, and the typo doesn't actually throw a syntax error, but it throws a kind of a PEP8 warning of non-standard, like a new variable was created and not used, right? That means you probably have a bug. If you've not tested your code and you've sent this out in parallel, then you're doing this wrong thing n times. And it's really hard once you've got your code in parallel to kind of debug what's going on because you don't get error statements back. So one of the keys that I want to try to do is make sure all my parallel code can be switched between serial and parallel easily and do most of my testing in the serial sense. All right, so one of the things that requires, though, is it requires good pickling. If any of you who've tried maybe using multiprocessing, you'll find that you get really excited by maybe what I showed about being able to go in parallel, but then you go try it yourself, and I would guess that out of 100 people, 90-some% of people who would try it on just some random code that they'd like to even if it's a small snippet of some code, they try to make it in parallel, it'll fail. Right? It fails because Python's pickler is not able to serialize the code. What essentially you need to do is replace the pickler. So here, I actually have this thing called check pickle, which is a nice little function. It comes from Dill, but it's a nice function, and what it does is it actually tests the serialization of a function across a process boundary. So some things like threading, it actually doesn't have to take the whole object across the process boundary, but multiprocessing on Unix and the Mac, Linux and the Mac, it doesn't have to take the whole object across the process boundary. It uses some shared memory space. On Windows, it does. It has to have a fully separated process space. And if you're going to parallel computing, again, the same issue is you're going across a different process space. So you want something to be able to be fully serializable, so it can be separated and jumped over to a different, maybe distributed or parallel process space. And this is a good checker for whether or not it's possible to do that. And so what I mean by pickling, for those of you who haven't seen it, it's essentially taking a list or some other object and converting it to a string like this, which has got a unique identifier. I mean, look, you can almost even read that. It says a list with an integer 1, integer 2, and integer 3 inside of it. And that's fairly readable. And here's squared, which is a function. And this is what Python does. It says, in main, I built the function squared. Okay, and it passes it by reference, which means it doesn't work from the interpreter. However, if this was in a file, it worked just fine. Right? So I'll try to pickle the list, and it works. And I try to pickle the function squared, which was built in the interpreter, and it fails. So all of a sudden, your multiprocessing that you'd be writing this code for doesn't work. I was very careful above to use a built-in, which was coming from a file, which is why the thing worked. So here's this sleepy squared. Here's sleepy squared. And again, what I'm going to do this time is from state. Okay, I'm going to check to see does sleepy squared pickle, and sleepy squared does pickle, and the reason it does is because we're only using time and time sleep, and it's coming from a file, right? Sleepy coming from a file works just fine because this was defined in a file, and Python can pickle it. So now the problem that creates is as soon as you have to, you should try that. You should try to write a function and fail, basically. And then you start to think about, okay, well, I want to use the parallel computing, so what I'm going to do is I'm going to have to modify my code to now work around this serialization issue. So we'll put that on the back burner for a second, but we'll see that you can do a lot of cool things with multiprocessing, and we want to be able to use it. So one of the things you could do is directly spawn off a process, pass a function like this function f to another process, here's a process where we pass off the function f and call it on arg's world. What this will do is it will create a hook to another process. We starts the job, basically spawns the process, calls function f, and then it waits here. It blocks and waits for the result to come in on join. With multiprocessing, it's using Python's pickle, so we can't do it in the interpreter. We have to do it in a file. We have to do it under main if name is main. And actually, I should mention that if you're on Windows, you additionally have to put this line in from multiprocessing freeze, import freeze support and call freeze support even before you do anything else. Okay, so here and multi-hello gives you a nice hello world, and that was run on another processor. So I'm going to talk about, so I already hinted at multi-threading versus multiple threads and the global interpreter lock, essentially that everything is locked. However, if you do go to shared memory, you get around essentially the global interpreter lock. You have to deal with it. You have to deal with thread locking. So here's shared state objects in multiprocessing. So some of these are essentially C objects. There's a package in Python called C-types, and what C-types allows you to do is C-types allows you to directly access C libraries and C functions, C libraries, C functions, and C objects from Python. You actually can call directly the Python C API with C-types and call Python at the C level. And one of the places that you see it used the most is in multiprocessing, where these things, value and array, are C-type shared memory values and C-type shared memory arrays. So if we wanted to do this shared memory parallelism as opposed to the functional parallelism that we've seen thus far, an example is here's a function f, and for I in range of length a, whatever we're going to pass in, a of I, we're going to flip the value to a minus I. So we build a value, and because we're essentially working in the C kind of domain, we have to give the indicators of what type of object it's going to be. So D is I'm forgetting, float, double, that's right, double, thank you. Double, and I is an int. So this is an integer array, that's a double a value, and we can build a process and run this function f. So this function will get serialized, it gets stored here in f, and then it's going to pass to it num and arg, and num is this shared memory value. So that means num is going to be shared between all the different processes, and so is arg. So they're all going to write to the same place, that it doesn't need to be copied everywhere. And then we do a start and a join. And what that's going to do is it's going to run it. This is done in another process, but then when we go back and look at num and r in the first main process, I can get value and I can print the array, and we could see that the values actually have been changed there. Okay, so that was done without having to ship the num and r back to the original process. So since it's shared across everywhere, we can just change it in one place. And because I wasn't having multiple processes hacking away at the same space, I didn't worry about locking it either. I didn't worry about setting a lock for competing values. So here's a manager. Basically, you can have the sharing of objects by proxy through a manager for shared objects. So I have a function which takes a D and an L. It's going to do L reverse, and D, the value, the first element is going to be set to 1, 2 to 2, and 2.5 to none. So what am I going to be doing? Looks like a dictionary and a list. So I've built manager, and manager dict and manager list are 2 items that I set to this shared object manager. And instead of using these built-ins like value and array, I've now got a shared dictionary and a shared list across the process space. And what I take is this target F, which calls this in the other process space, on D and L. And then when I do a start and a join, I can see that I actually change these values in D and L without having to pull them back into space. That's actually, I guess I should emphasize that when you spawn something in Python to another process, what it's doing is it's making a copy of the data and it's making a copy of the function. It's serializing both of them and sending them off to the other process space. So if you're to build a class and you expect that you're going to change an attribute within a class when you send it off to another processor, it will. It'll make a copy of that instance of a class, change the attribute in the other process space. But if you don't return the value that you change, you'll lose it because it gets changed in the other process space and then goes away. You're not sharing the object between the process space. And to do that, you have to use things like this manager. You have to use these shared memory array values. So if you want to do that, then that's you have to work with these shared memory objects, or else you have to return the value you're interested in. All right, so there's if you want to do NumPy, there's a formula here for doing NumPy. There's shared C types and C types lib. Both of these are necessary for doing shared arrays with NumPy. So you can do shared C types and get a raw array, an integer array of length 4. And you do shared C types lib as array and convert this raw array into a NumPy array. And then we can fill certain elements of the array and fill certain elements of the array in 2 different processes. And I'm not worried about them stepping on each other because I'm having them fill different elements. So I'm not locking it. Otherwise, I should be locking these things down. And then I start both processes, so it writes to the arrays in 2 separate processes, and then I do 2 joins to gather up the processes and shut them down. And then we could see the value of the array that's been changed in the local memory space, and it's changed it without having to pull these things back. So it's a little bit more complex to set up a NumPy array, but you can do NumPy arrays too. All right, so I mentioned threading and locks, and what you'll see is this guy, worker, what he's going to do is sleep for some unknown amount of time, randomly generated, get the current process name, and then say, hey, I'm this guy. I'm this current process. And then we're going to do a loop So it spawns two processes, spawns two workers. They have slightly different argument. It's going to start. It's going to run both of these in parallel. And then what I want to do is close up the ones that are still active by this time. So I do that. And it looks like worker 1 finished before worker 0. So I essentially wrote a for loop where it's running the payload in parallel, spawning out two processes and running the payload in parallel. You don't necessarily have to do that yourself. You probably shouldn't write this for loop when you have a pool that's available, unless you're going to do something interesting. Most people, when they get into multiprocessing, they just start using pools. But you should be aware that the process is available for things. If it's hard to work with a pool, you can go down and do more detailed things within a process. So there's queues as well. So I have a queue that I can set up, get for passing the queue in, get the value from the queue, print the object I pull off of the queue, and on this side, I'm going to be sending a message, hello, hello. I'm going to print something I'm sending to the parent, and I do send, which is in the other end of a queue, a process, and then I'm going to receive from this process. So you can send and receive, and also a queue you can get. So there's a pipe essentially to another process with send and receive, and a queue with get and put. So I'm building a queue here in multiprocessing queue. I'm building a pipe here with multiprocessing process. And the thing I pass is the queue here to my queue worker. And when I say start, it will run the thing in this other process. So it runs the thing in this other process, the queue worker, and it goes to right here and it waits. And get is blocking, so it's going to wait right here at the get. And what's it going to wait for? It's going to wait for my signal over here from the other process. So this main process is moving forward. It's kind of schizophrenic in that you have code that's stopped here in one process and code that's moving forward here in another one. You say, I'm putting this on the queue, and then put into the queue put, and then what happens as soon as you put into the queue put, then it executes this code, it grabs it from get, executes this code. This still moves on, and then it'll block here at join. Okay, so join is blocking for the main queue to wait until the queue worker is done, and the queue worker is blocking here, waiting for something to get put on the pipe. And again, here's on the queue, here's a pipe where we have two ends. Instead of just dealing with the main connection, we now can have a have a pipe where we have a parent connection and a child connection. So you can pass through one process a child connection, start, and say receive. And so right here, this is going to block and wait to get something from the child connection or whatever's been spawned out to this P worker. And here, the first thing the P worker is going to do is send a message and then hit receive and wait. So this will work all the way down to send. This guy's going to wait. He'll receive hello, 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 and then he'll move on. And then he waits up at receive, and down here, send the message. It's going to send a message back to the worker. Then he'll get the message and then print out something. And then we'll do a date time and say we've finished, and then do a join where it'll block and wait for the other end of the pipe, the process on the other end of the pipe to finish. Right? So that's code being executed at several places. So there's basically this code being done across several processes. So you have the pipe worker sends hello, hello to the parent, then the child receives, then we receive hello, hello, hello from the child. We're sending a serialized object basically to the child. The child got this object from the parent, printed it out, unpickled it to see we sent a list across the pipe, basically. And then we finished and joined the processes back together, shutting down the parallel portions of it. So, like I said, this is actually details people don't tend to go into when they start parallel computing. They get into working with pools, which we'll see in just a little bit, but if you have to work on these things, they are there in the multiprocessing library. Here's a lock, and what that means is we can build a lock and enforce synchronization if you have something that needs to be the only thing unique running in process space. So you have multiple processes that are running, and you're going to be writing on some of this shared memory space. What you can do is put lock acquire on top of this piece of code that you have to have run in an isolated sense in parallel. And then that is the only code that will be run in terms of everything else that's been spawned with it. And then you have lock release, and then it's free to run asynchronously where they're all gonna where they can all run at the same time. So here's taking a lock, and we're putting several copies of the lock onto several processes. And there's 5 different processes that are going to be spawned at the same time. And what's going to happen is when one of them gets down to lock acquire, it'll run this for loop in parallel and then release the lock and then allow the other jobs to go through those same things. So you could see what happens is this ran in parallel, but notice that it ran all the zeros first, all the ones, all the twos, all the threes, and all the fours. And that's because it spawned them in parallel, and zeros were spawned first, and it acquired the lock. And then it locked out all of the other codes from running in parallel, and essentially went through the for loop, and as soon as it was done, then 1 was next in line. So it's not terribly parallel, but it's equally as parallel as Python's thread parallel is that you get with the lock, global interpreter lock. So okay, there's an event which is another thing you could do that's like a lock, except all it does is it says I'm going to run the code down to a point where it says wait, and I'm going to wait. And all that does is if you have to have 2 pieces of code executed at the same time or a particular sequence in parallel, you can set up one of these events. I build an event, I pass it to the process, and then the code will actually wait. That process will wait at that point until it hits a signal, and the signal is set. When you get set called, then it will release on wait, and all the codes will run. So what this did is it held all the processes right here, and then when I called set, then it let them go and let them finish waiting. Okay, so high-level processes, high-level structures from multiprocessing are like pool and map. So here's a function called random mean. It imports Numpy, and it rounds the mean of some random integer that's actually it's going to do 10,000 of them. And it's going to, so that's a bunch of numbers that are going to be created, and we're going to get the random mean of those numbers. And the reason I put the import inside of random mean is to aid pickling, essentially. You have to make your functions, if you have your functions and your functions are going to be sent across a process boundary, they have to be encapsulated. So it's much harder to encapsulate, it's much harder to send a function, much harder to pickle a function that you have things that are defined in the enclosing namespace as opposed to its own namespace. And I mentioned earlier that it's more costly to do imports, right? It's more costly to do imports, so you only want to do them once, which is why you're often told what you want to do is put the import outside of the function, right? Because it gets run when the module gets loaded. But if you're going to be sending something across the process boundary, that's where NP or Numpy is defined. And if you put that import on the outside, it may not work. It may not work because that function will get sent over the wire onto another process space, and it hits NP mean, and it says, what's NP? Well, it's not in my local space, so I'll go up to my enclosing process space, and it's not there. And you have failure. Okay, so it may be slower in serial to run to put the import statement on the inside, but it works if you're going to be sending it off to parallel. So the key is encapsulation of all the defined variable names. Now, some serializers can actually go and grab stuff from your global namespace. However, the safest thing to do is always make your variable definitions, your functions have their variable definitions enclosed. So X is defined locally and NP is defined locally here as well. And then when I do something like this, in parallel, what am I doing? I'm building a pool, and I'm taking that map function and calling random mean 10 times, or 9 times, 10 times, and doing that. So each one of those calls is done on a different processor, and then getting the results back in terms of a list. And you can see my results there. And here's apply also. Apply takes that random mean and basically calls it on just one element. And it's the same as if I had done random mean of 100, but it's now done on another processor. And I do my close and my join. So there's several variants to map. There's IMAP, which is an iterator, and IMAP unordered. And what that means is you don't have to be blocking like I saw above in map. You can build a map iterator, which it'll spawn off jobs to another process, and IMAP will wait for them in order to come back. You spawn them out, but when you say next, 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 you can start to do processing with results as they come back one by one in order. And IMAP unordered gives you these in an unordered sense, that it basically, if you don't care about the order, it'll get the results back as soon as you get them back and print them out. So here, what we were able to do is we can look at ready, which lets us know whether or not, so map async, what map async is doing is it's a blocking map where it's asynchronous, and you can spawn it out to another process. It lets you go forward in the code, so I can print waiting, and I can do ready to check and see whether or not the results have finished. And the only thing I can do from an asynchronous one is get, which is a blocking map, but you don't have to do that until you until you know it's ready. So the dots that are printed out there are done waiting for the going through this for loop or while loop, waiting for the results to come back, and then once the results are ready, they're finished. Then I can do the get and just pull the results back from the other process. And you could do the same thing in the one-dimensional case to a single process with apply async. But I guess I didn't run this one. one of the nice things here is this actually works on sending the job out, and if you don't care on the order it comes back, I can run it in a for loop. There's my IMAP unordered being run in a for loop where it's pulling off one result at a time whenever it's finished with the result. So IMAP unordered can be one of the fastest ways you can do parallel computing because it doesn't block anywhere. It's only as soon as you get a result done, it'll move on to the next one. The impact of it, of course, is you lose the order of the results. Okay, so a thing to be aware of is random number generators. Here we have walk, which is performing a random walk, and it's doing random uniform, which is a Numpy random function, and then doing some other stuff. And I'm going to vectorize the random walk because I just didn't bother to write this in parallel fully. I didn't write this in Numpy terms fully, basically. And now I have this parallel walk, and I'm going to call parallel walk on Numpy, an array of Numpy zeros. I'm going to do it again, except put this walk inside of a list comprehension. And I'm going to do it again by calling walk inside of a multiprocessing map. All of them again over these zeros. And what you see is a problem down with the parallel map. You could see that for vectorize it works fine. For the list comprehension, it works fine. But when you do the multiprocessing, on walk, that function up there where it does NP random uniform, that does not look random, right? You get 27 everywhere except one of the results. So what's going on? That's right. It's taking the random number. So what it's really doing is NumPy random has a random state. It has a random number state that is spawned off the clock. And it's not that it's being done at the same time, exactly the same time, but that's a good idea. It's close. It's taking a copy of the current random number seed, and it's passing it out to all the different copied objects on all the different nodes, and then the next random number is the same everywhere. Okay, so you have to worry about things like that. Is the seed is being copied and passed out everywhere. So when you do NumPy random, and actually even if you do random, you get the same thing that happens. So how do you get around that? You have to have a good state pickling, and that's random seed or random state. So these little functions you could use. This random seed sets the seed for calls to random, and that will allow you to always reproduce the same results when you have randomness. And the opposite is random state. And this little function here, what it'll do is ensure that when you're calling random numbers, you're actually getting a new random number for either NumPy or Python random within the other process. And what that does is it actually generates a new random number generator for that particular process. So instead of taking a copy of the random number generator, it builds a new random number generator. And it's a little bit of code, but it's what's required to be able to get a different value in NumPy random. Yeah.
So where you were showing us the error where it was all 27s,
Yeah.
that would still be the case even if we moved the import of NumPy inside that?
Yes.
Yeah, okay.
You will get that. Again, because it's NumPy's default seed that's being passed along, basically. So you have to redo the random seed, which is what this function is doing. It's saying generate your own seed either from 0 or from time.time, and then seed the random number generator, and then you'll get different results. That's a common issue. Here's I mentioned the issue. So there's random number generator, which is an issue. Copying is an issue, right? You don't expect that what it's going to do is make copies of things, so you have to work on building these shared memory objects. Shared memory objects can be really fast, but you have to worry about thread locking. I showed you how to do the thread locking. And the other big issue is serialization. You see all of this and think, well, it's neat, and I'd like to do it. But if you're to write with multiprocessing, I want to build a pool and then send a simple lambda function like this, x squared, it will fail. Okay? And that should show you even simple patterns like a lambda function or a class method, they'll fail with multiprocessing. So there's a fork of multiprocessing called multiprocess that essentially uses a better serializer that can ship most of the things that you build, most of the different class structures and whatever you build in, and also work from the interpreter. And it enables you to do pretty much your normal, either good, well-tuned serial code and send it off in parallel, or your junky, your poorly coded serial code in parallel. The lambda fails in Python because Python can't serialize the lambda. I mean, it's just the number of objects that the Python knows how to serialize by default is very minimal. And the number of coding structures that that Python knows how to serialize by default is minimal. So the real reason is it ships functions by name, by reference. It ships functions by reference. So it has to have a name defined within a module. And Lambda doesn't have a name. It's built in main and it doesn't have a name. But you can serialize it. And so I could also have serialized squared with this thing too, which was built in main. So what you want to do with this is you want to be able to, the reason why I'm saying use multiprocess as opposed to use multiprocessing and then fight with modifying your code is that you don't want to modify your code. You want your serial code to work exactly the same way as it works in parallel, because all the sweat equity you put into making your code fast in serial, if it doesn't just imminently become parallel by switching a map or using an apply, then you lose all that work. You have to rewrite it for parallel. And you don't want to have to maintain the parallel version of your code versus the serial version of your code. You want to be able to just change like this, the map function, right? This, without the pool in front of it, would be serial, and then with that map function, it's parallel. Now it looks amazingly simple and obvious, right? But it's actually not the decision a lot of people make. They'll come to the point where they can't serialize something, and then they rewrite their code so it works in parallel, and then you lose all the work you did ahead of time, and you can't go back to the serial case easily. So this is what you want to do. So I had another little exercise of something you could try with several different variants of hierarchical parallelism, but you can just play with that yourself. It's a password cracker. So in the same sense, there's object-based serialism for distributed computing with Parallel Python. And what Parallel Python will give you is the ability to type code like this, squared, set up a server, submit a job to a server. So we're submitting squared to the server. and then we're going to wait blocking for the results. Okay, so this is asynchronous distributed parallel computing. Similar to 0MQ, Parallel Python works similarly to 0MQ, which I'm not showing. And then you print the result that you get at the end, and you're done. So this server is actually a local server, but you can say a server can take localhost and then a port number, or it can take remote and then a port number. So remote and a port number would be the URL address and port number of a remote where you want to farm the job to. You want to make a connection to that remote host. And the reason I like localhost 800 or localhost and a port number is you can actually set up an SSH tunnel back to a particular port and then use PP to pipe to localhost and a particular port, and then it'll send it off across as an SSH tunnel to another machine. So simple as that to be able to do secure parallel programming. Now, I'm using PPFT, which is a fork of Parallel Python, again to get serialization. And this, even though it's a local job, since I just set up a server and I didn't send to another machine, this will work equally as well to send it off to a distributed node and get a result back. Okay, so that's just, and I don't have to demonstrate Parallel Python too much more, because essentially what you get out of it is that's how you make a connection, and that's how you do asynchronous map. Instead of a get like you got from multiprocessing, it's wait, but it's ultimately the same thing. And you think, wouldn't that be nice to have it rolled up into the same interface, and so then you don't have to remember what's what, and you get a pool of distributed workers or a pool of parallel workers. The nice thing is, if you want to mix and have some distributed and some parallel, and you want to build upon it without actually having to change your code again for distributed or parallel because they have different names, then there's this package called Pathos, which, again, it's my fault, since it's my package, that it's not supported in Python 3 yet, but it provides a common API for distributed and parallel computing, multiprocessing, Parallel Python, etc. And one of the bummers that multiprocessing has, which I didn't mention, is the maps are different. The maps are single argument maps. They only take a single argument. They don't take multiple arguments. Python's normal map takes multiple arguments. So if you have a function that takes multiple arguments, what do you do to have it run in parallel? Star map, right? Star map, or you put it into a tuple. But yes, you can do it, but what you end up doing is you're changing your code to go in parallel. And even though it's that little simple thing, you start having you forking a variant of your code, whether it's running in parallel or not. You actually don't want to do that. So what Pathos does is smooth out those tricks to provide you with the same code, regardless whether it's serial, parallel, processes, or distributed. So there's a serial pool, parallel pool, process pool, and thread pool. And we're going to do this sum squared in parallel. And it's going to go through the different pools. For pool in serial, do a blocking serial map with 2 arguments, then close and join. The parallel pool, which is across, well, it would be on another server, and then processing across process, and then threads across threads. And this is the way you want to have your code written. So, like going from map to parallel map, it was very easy to just drop that element in. Here, I even give serial pool. The reason I give serial pool is you don't have to change any code at all. You just change the change the pool, and you'll get the same code underneath that works by immediately flipping this to a different parallel backend. All right, so that means natural programming constructs are able to be used in parallel code. So here's working over prime numbers. We can check if this is prime. We can do something like math, square root, floor, this for loop here. This guy it looks like code you might write to check and see if it's a prime number, and I can test this by passing this off to parallel. Notice the things that I've done here is import math on the inside because I know I'm going to be sending this job out in parallel. All right, so I can make them a little sleepy, which means they take some time, and I also will put the imports of sleep on the inside. So these are adds that take a while. So now this is going to run. I'm going to take a process pool, and it's going to run this test with the process pool, and you can say with pool as my pool, do a asynchronous map, so that's map async for sleep add on some inputs, get my result, and then with pool as pool2, so it just does the close and join for you, and then do another asynchronous map on add 2, and there's on 3 for number in prime in izip, so I'm even doing an iterator with the pool imap on the inside, so that's another iterator. This is kind of like code that you would program in Python if you're trying to do fast things with in serial Python with iterators. There's an izip with a pool on the inside and an imap, and that code is parallel code. That code is parallel because there's the pool at 2 levels nonetheless. It's a pool inside of a with statement that closes it out for you inside of an izip, and you wouldn't want to have to change that code. So that code will fail in normal Python. You don't want to have to change that structure. You just want to be able to switch out the pool and go right to parallel. And again, what I know we're not going to have time for it, but I'm going to encourage you to go back to this password cracker because it gives several different structures that you can play with to check the time it takes for hierarchical parallelism. Here's hierarchical computing, basically. So 2 different pools, a process pool and a thread pool, and there's a map, an asynchronous map of a map function, which is a process pool map of a thread map calling sine and cosine, and then doing a get. So this looks very much like the bad nested loops that you might do inside of list comprehensions or a map above, and you should be able to run that in parallel, which I just did. Okay, so the idea is not going to have to change your code to go to parallel. And that way, your efficiency is in the code you write, at the beginning of this serial code, the code you test and write, and then when you go to parallel, you don't have to do anything except flip the back end and then test it again. You want to test it for speed. The thing you want to do is, now that you have the ability to switch between a lot of different parallel backends without changing your code, you just test it and see ultimately which way it becomes the fastest, and it's actually very easy to get code that's high performance, as opposed to changing your code to go to parallel and then not having a reference to go against, which is a reason why you want to follow this path. All right, so apparently I won't go to the part with the tunnels, which I talked about, and the only thing that was that's left essentially is the large-scale cluster computing, which again, I'll come back. It's MPI for Pi, but I would come back to the same thing exactly as you get the same structure. If you can get a pool structure, which this package Paina provides, it gives you the Pathos interface essentially, and then you can flip between launching jobs on clusters and with MPI, again without changing your code and without changing the interface. So it's easy to apply the simple rules of timing your code, testing your code in serial, and then switching back and forth and checking what happens when you send it off in parallel. You don't have to be intelligent. You just have to use some very basic tools. Actually, less intelligence in parallel computing is good. Stupid is easily parallel, and intelligence is not. All right. Well, I appreciate I appreciate the attention on this, and there is more on the MPI page and whatnot, but you have the links to the notebooks. So thanks. Oh, is it? Excellent. I thought it was 12. All right. Well, how about that? I got an encore then. Thank you. That's great. So then I will do more. I've never done that before. Okay. So you see the idea of going into going to work in this way, that we can just switch between the different processes, and here's actually the code. Here's the code with Parallel Python, where I'm setting up a server on a particular port from the command line. I might run that on my other server or on my local host, and you can see that if I say servers localhost 800, then what it's going to be doing is it's going to be distributing the jobs based on workload between the two servers. The one server is itself, the local process space, and the second one is localhost 800, which is whatever thing is connected at the port 800. That could be a distributed job being farmed out through SSH to another host, or I could have put the URI basically here, and you could see that it's in this case sending out 65% of the jobs to whatever's sitting at localhost 800 here. That's faster. There is a way you can set it to have no local jobs, and I believe that nodes is 0, if I remember correctly. So there's other things that do similar jobs, 0MQ, Pyro, and RPC, but they don't give you the same interface all the way through. And there's, if you wanted to set up a connection, so there's Pathos, which has SSH tunneling, Paramiko also has SSH tunneling, and the whole point is to set up a connection, set up a secure tunnel, or set up a connection that's connecting a local port to a remote port, so that when you send the job to your local host at port 800, it actually fires the job off to the remote host to run the code, which makes it very easy to run a job on a supercomputer or a cluster somewhere. Right? So you can use could use this to farm out jobs on a cluster without actually being on the cluster. And that's here's running a secure pipe where we're running a job through SSH on another machine. For for cluster computing, there's a number of options. Basically, there's MPI, which we want to really look at MPI for Pi. MPI for Pi is the best supported of the MPI packages in Python. So that's the one to use. And GPUs are PyOpenCL and PyCUDA. Cloud computing, it used to be PyCloud, but now it's called Cloud, and you have to pay for it. PyCloud was free. Cloud is a pay-for service. There's Mr. Job, which is, I think, for EC2, if I remember correctly. And there's Apache's Mesos, Spark, Hadoop, Zookeeper kind of mess, which actually has gotten a lot better and well supported. So for cloud computing, there's a couple options. For GPUs, again, GPUs and MPI, very difficult to build. Very difficult to build these guys. And however, once you get them built, they can have a high payoff because the MPI is very fast, C-level parallelism across a cluster, where you can work across cluster blades. GPU is parallelism across a graphics card. So working on MPI for Pi. Again, the forewarning is it's typically not an easy install. Actually, it didn't pip install for the longest time, and I don't even know if it still does. Yes.
You can get it too.
Yes. See, you can get it to. That's I've had it install with a pip install as well. In my package, Paina kind of tries to fix some of this stuff. So I've actually worked with Lissandro to pull in some of the easier install stuff for different platforms, but it's still hard. The big problem is MPI, right? It's if you don't have OpenMPI installed, then good luck. It needs MPI.h, which means you're compiling C code. So this is a good test to make sure that you actually have MPI code running, and I have this running. I built this code, and you could see that MPI for Pi, what you do is you import an MPI instance where we're going to call get size, get rank, get processor name. These are all things about the instance I'm going to be running on, and then say hello world. And so the issue here with running this code is, look at it. It's MPI exec for 4 copies of running Python 2.7 running hello MPI for Pi. The syntax to get that running is not Python. We're not actually running Python there. We're running MPI exec to then run Python to then run our Python script. So that's the syntax for running. We're using the MPI launcher to run Python to possibly have shared memory across some of these processes. So you're not going in your normal workflow. How would you build on top of MPI exec if you wanted to do something where that is just part of your script? You can't. Okay, so that's one of the already limiting things about MPI. Although this is it's running in very fast parallel. And the coding becomes very difficult if you're down in the weeds here. It's kind of schizophrenic. It's multiple personalities, let's say. It's multiple nodes. What you have is MPI for Pi, import MPI com world to get where you are. What rank we're on is the number of the node we're on. And rank 0 is the head node. So if we're on the head node, this code this same code is going to get passed out to all the different nodes. So what we're saying is if you're on the head node, do this, and then send data to node 1 with the unique identifier, and then send more data to node 2 with this unique identifier. And then if you're on node 1, then receive from node 0 with this particular identifier our data. And then if you're on node 2, receive from node 0 with the same particular identifier and get a result. Looks painful, right? It is. It looks painful. That's when I did multiprocessing just a little bit ago, and I was doing the bit about pipes and sending things across pipes and locks, you've got the same thing going on here, but worse, right? You have to specify source and destination and unique identifiers, and there's not only a separate function to be run, because it's not going to just run a separate function, it's going to pass the entire code file over. You can't just pass a function off. You have to pass the entire code itself off, because you're running it as MPI exec with Python 2.7 and then that file. So you have to give indicators to each of the different nodes which bit of code it's going to run. And if you don't, it gets executed by all the nodes. Okay, so sometimes you want code to get executed by all the nodes, and sometimes you don't, and you can figure out which node you want to have run by the rank. So this now, oops, what do I not have? I probably didn't build, I didn't do that, and then that. Okay, so what that does is now I sent this data with 0, and then I shipped it off to node 1 and 2, and you could see the print isn't respected terribly well because it's getting both prints activated at the same time, and you're getting the second print stuck inside of the first one, but that's just printing. It's actually doing the job in asynchronous parallel. So yuck, right? But this is how you do it. Here's non-blocking communication. Non-blocking communication, there's I send and I receive, and there's wait all, basically wait for all of those things to be done. And here you have sending data, rank, so the head node sent data, the other node sent data, the head node got data, and the other node got the data. But you see, it's still the same thing basically as, it's basically the same thing as multiprocess has with send and receive or put and get all the way through, except what you have to do is identify destination, source, and a tag. And again, the code is potentially going to be executed by one or more of the machines. So here's another pattern if you want scatter. So this is like scatter gather, which I won't do. Here's broadcasting, which is another pattern. But it looks like we have to write most of this ourselves, which is a bit of a bummer, right? I mean, if I want parallel computing, I don't necessarily want to have to get into these weeds. I want to do like I did in multiprocessing and just go to pool, right? And give me my parallel computing without having to work so hard. So this is good if you want the customization. And another issue that MPI has is, again, it's got to do serialization. So there's a little trick that MPI has built into it that if you want to use a different serializer, you can put a different serializer like Dill or Cloud Pickle as the serializer, and then you get the good serialization to the other package, to MPI for Pi. So another thing you can do that that's not a very common thing is you want to send your code off to a scheduler. You can do this with MPI for Pi by building a job script. So a job script has things like PBS, number of nodes equals 1, parallel processor nodes 4, processors per node. You can say wall time. So this is what a job script file looks like. And then if you run that job script, you see it has exec Python and then hello MPI for Pi. It will then run that job on the scheduler. So far there's a bummer, right? It's basically we're not running Python from Python anymore. We're running Python from the command line, where we're not in our normal workflow, which means this is the be all and end all at the top level of MPI, which is unfortunate. Sometimes you'd like to have that be part of your workflow. And in the last very few minutes I have, there is this package which is Pyena, which is basically the MPI version of Pathos. It's not as well supported as some of the other packages are, but there's not much to it actually. It's just, it builds a loop. It builds a workflow environment. It builds a pool, and it builds a higher level multiprocess style high level interface around MPI. So you can actually call multiprocessing from Python, from the interpreter, from main, and call it with maps and pipes, and call out to schedulers. That essentially, what it does is it builds the job files and it spawns off through sub-processing, kind of pseudo command line into another process space and spawns out the MPI. What that does is basically allows you to build on top of MPI for Pi and work with schedulers and whatnot. So here is an MPI launcher that's just going to run an 8-way MPI job. You can, since there's all these different strategies like scatter or broadcast, you can change the strategy by changing the pool strategy. There's scatter strategy. Do we want to serialize the source code or do we want to serialize the objects? So you can actually dump to extracted serialized source code, or you can, which is what Parallel Python does, PP extracts source code. Or use the scatter or not. And so these maps are actually maps that are being run in 8-way MPI parallel from Python, from the same process space. So we can build this guy and we run it, and these guys are now being done without actually having to go to the command line and do MPI exec, and which is what you want to then be able to build on top of it. And then it follows the same paradigm as what we had before, which is I don't want to have to write from the command line. I don't want to have to change my code at all to go to parallel. So you could do more of the same with, so Pyena and IPython parallel kind of have a similar thing that they do. You can do IP cluster MPI exec in IPython, and Pyena isn't. Pyena and Pathos are older packages. They're like 10 and 12 years old. So there's been more recent ones that are a little less robust, but have broader support. And you could see a similar thing being done here with IPython to send it off on MPI for Pi. But again, this is what it's doing is it actually doing a command line trick to run the command line from IPython. And down here, here's some examples of using the Torque scheduler and different schedulers to run code on your production cluster. So Torque on a particular queue with a time limit. All the things that you would feed into your job file feed into your scheduler instance, and then you can use a mapper. You could pick your mapper and set your scheduler instance, and then your map will map across your scheduler out and farm your jobs out on your cluster. And again, what that does is it allows you to write your code in the same way as before, where you don't have to change your serial code. And now you can just rely on timing and fine-tuning your serial code, and you have to now do configurations of timing across the different setups, like how many processes per node do I want, right? How many resources do I want? What size of pool do I want to look at? All right, so now that I've taken the extra 20 minutes, I appreciate your guys' attention again, and thanks.